Okay, this is where we were in our last video. I want to look at some examples of finding square roots, cube roots, fourth root, and so on of complex numbers. Let me just erase the board, or most of it as it is. So we start with a clean board. I'll copy that because I want it and paste it back. Now, what I want you to do, so hopefully you made some notes on the previous video before I erased it. If z, the complex number z is 3 plus j4, find the square root of z. Alright? Now, we're going to convert this from rectangular to polar form and then use De Moivre's theorem. Here, the magnitude of a complex number, and by the way, let me just do some visual representation of it. Right? The complex number is 3 plus j4. So if it's here, then you go out 3 and go up 4. So you want r. I want to find the angle theta. Right? Draw this a bit larger. I could get a neater looking circle. Alright, I have my circle here. Good. So here now, what we have is this Argand diagram representing the complex number. You have theta, you have r. Remember, this width is 3 and this height is 4. Alright? So r, the hypotenuse of this right angle triangle, r squared, is equal to one of the side 3 squared plus the other side 4 squared. If you work it out, you're going to get r squared is 9 plus 16. 9 plus 16 is 25. And then r is the square root of 25, which is 5. Could work it out to show that that is so. R will be 5. Alright? Now theta is going to be tan inverse. Remember, tan theta is the opposite over the adjacent, 4 over 3. So theta is tan inverse of 4 over 3, which is, let's get our calculator and see what will happen here. I want a calculator. Alright. So, one tan inverse. Tan inverse, where's the inverse thing? Where's the inverse on this thing again? I used the tan inverse on this before, you know. Tan inverse of open bracket 4 over 3 close bracket equal 53.13. 53.13. Remember, we're working in degrees here, but you could very well have a question that asks you to work it out in radians, right? But let's work in degrees for now. Alright. Now, this complex number in polar form is 5 cos 53.13 plus j sine 53.13, right? If you find the cos of 53.13 and multiply it by 5, you're going to get 3, right? And then if you find the sine of 53.13 and multiply by 5, you're going to get 4. Alright? But anyway, this is the complex number. Now, what you are going to do is find the square root of this complex number. Now, the square root of z is going to be same thing as z to the power of half. So, it's going to be 5 to the half, bracket, you have cos half of 53.13 plus j sine half of 53 point, where the bracket, half 53.13. So that's what you have. It's the same as following the formula for De Morph's theorem, which says z to the power of n is equal to r to the n cos n, let me rewrite that, cos n theta plus j sine n theta, right? Remember that. So, therefore, the square root of z, as we have here, is 5 to the half, which essentially is the square root of 5, cos 53.13 over 2. When you say half of something, it's the same as this thing over 2, plus j sine 53.13 over 2, right? So the square root of z is going to be, what's the square root of 5 again? Let's get that. We want the square root of 5. So it's going to be clear. Square root of 5 equal 2.236. Let's keep it to 3 decimal places since we haven't reached the answer yet. 2.236. So it's 2.236 cos, now 53.13 over 2. What is that? 53.13 divided by 2 equal 26.565. 26.565 plus j sine 26.565. Alright? Now remember, we're finding the first square root here. The first square root would be just the square root itself, the number itself, the square root itself. So that is the first square root. Now we can call the square root z1. We'll have 2 square roots because guess what? We will have to have the circle divided into 2 parts, right? To find one of the square roots. So we'll soon turn this back into into rectangular form. But let's find the square root 2. So the square root of z number 2, right? Remember, the magnitude remains the same, right? The magnitude will remain the same. It's going to be a new circle, by the way. But we'll come to that. We'll come to seeing what happened. 2.236, and then you have cos. Now remember, we need to circle this thing. 26.565 plus. Now we're going to rotate it. Plus what? What angle? 360 over 2. Because remember, we have 180 degrees. 360 over 2. There will be 2's. I keep referring to this. Let me make a copy of it, because this is not the square root. The square root will be in a new circle, right? The magnitude is smaller, so let me make this smaller. Right? But we'll soon be using it. So here, plus 180, this is a cos, plus j sine 26.565 plus 360 over 2, which is plus 180, right? So what we have is 2.236 cos. All right, so 26.565 plus 180. Let's reach for our calculator again. All right, 26.565 plus 360 over 2, which is plus 180, gives us 206.565. So it is 206.565 plus j sine 206.565. Alright? So those are what we have. Now let's change Z1 and Z2 into rectangular form. So square root 1 is going to be, we'd have to do the multiplication here, right? And the trigonometry, of course. So let's see how this goes. We're going to have Z1. Let's clear the screen, the calculator. 2.236 times, this is in degree, right? The cosine of 26.565 equal, which is 2, all right? And then we have 2.236 again times the sine of 26.565 equal 1. So it's 2 plus j1. So it's 2 plus j1. And the square root of z, the second square root of z, we want to find out what that is now. Calculator again. So this is 206. It's going to be 2.236 times the cosine of 206.565. 206.565 equal negative 2, and then 2.236 again. 2.2, oh no, that's 2 points. Where's the backspace? Okay, 2.236. That's 2.236 sine times the sine of 206.565 equal -1. So it's -2 minus j. So we have -2 minus j. Alright, so let's bring in the circle now and see how we can represent these things. So here we would go out to 2 plus 1j, alright? So we would have 2 to the right, 1j up, okay? That's what we have there. And the other one is -2 minus 1j, straight line. Doesn't really look like a straight line, but it should be. Let's draw our x and y axis here. So what we have then, the 26.565 degrees would be this angle here, right? That is for theta 1 equal 26.565 degrees. And then when we add the 26.565 to 180, we have the second angle here. So theta for 2 is this, which is 206.565 degrees. So as you see, the square root, it divides the thing there, the circle, the unit circle. Well, in this case, it's not unit anymore. It divides the circle into 2 halves separated by 180 degrees. In this case, finding the square root, the second square root, the first square root, this angle over 2 would be multiplied by 0. Okay, it would be 0 for the first square root. In the second square root, you multiply it by 1. So you have 1 times 360 over 2. Right? I'm telling you, because I've seen the formula somewhere. So if I can remember it, the nth root of z is equal to the nth root of r times cos theta over n plus k 360 over n plus j times sine theta over n plus k by 360 over n. If you're working in radians, the 360 would be 2 pi, right? So this would be the nth root of r times cos. If you add them together, you get theta plus 360k over n. Remember, these are in brackets. You're finding the sine of all of this, plus j sine theta plus 360k over n. Alright? For the first root, k is 0, so you don't have to worry about it. The 360 would disappear. For the second root, k would be 1. For the third root, k would be 2, and so on and so forth. Alright? So here, this is what you'll have. You would see this formula in books on the internet somewhere, right? But this is where it comes from, right? You have 2 square roots, so it divides the 360 into 2 parts, or in the case of radians, the 2 pi into 2 parts. If it was cube roots, there would be 3 of them, and you divide the 360 by 3, or the 2 pi by 3, and so on. Alright, so in fact, I'm planning in the next video to find the cube roots, the 3 cube roots of this. But in the meantime, I'm going to ask you to do that before you watch the next video. So I'll see you.